Hello everyone. In this lecture, I will discuss some basic terms that is used in coordination chemistry. So before proceeding this chapter, that is a coordination chemistry, it is necessary to define and understand the general terms that is used in describing the coordination compound. So the first term that is used is a complex ion. So this is an electrically charged ion which consists of an ion that is mostly metal is used, which is directly linked to a group of neutral molecules or ions. The most common example or the most common complex ions, they are the metal central complex ions. For example, if you see this copper complex, in this copper complex, the copper metal is attached to a neutral ammonia molecules. If you see the second cobalt example, in this cobalt, the metal cobalt, that is cobalt 2 positive, is attached to a negative ion, that is Cl negative, as well as a neutral molecule, that is NH3. So when simple ion form a complex ion, they lose their individual properties and acquire the properties characteristic of the complex ion. The next term that is used in coordination chemistry is a coordination compound. So coordination compound is a complex compound in which the number of ions or molecules attached to the central metal atom is beyond the number possible on the basis of electrovalent or covalent bonding. If you see this complex, the copper complex, now in this the oxidation state of copper is +2, which is satisfied by 2 negative charges of sulfate ion, that is SO4 2 negative. The 4 ammonia molecules, they are coordinated to copper ion. Now how this ammonia molecules is coordinated to copper ion? In ammonia molecule there is a nitrogen atom, and each nitrogen atom they consist a lone pair of electron. So nitrogen atom of each ammonia molecule, it donates its lone pair of electron to copper ion, that is U2 plus ion. Similarly, in platinum complex, the 6 ammonia molecules, they are coordinated to platinum Pt4 plus ion. Now types of coordination compounds. Coordination compounds are mainly of two types. One is neutral compound, in which there is no charge on the compound, like FeCO5. This is a neutral compound as there is no charge outside this bracket, there is no charge on this complex, so this is a neutral compound. Next is ionic compound. In ionic compound, which consists of ions in which at least one is a complex ion. Now this ion may be cation or anion in nature. If the anion is complex and the cation is simple in nature, it is called a anionic complex. So this is the example of an ionic complex, K4 FeCN6, that is potassium hexacyanoferrate. Okay, so what happened in this? In this, the complex, that is FeCN6, the complex ion, is anion. That's why it is example of a anionic complex. If the cation is complex and the anion is simple in nature, it is called a cationic complex. If you see this example, this is a copper complex in which copper, that is the compound, the complex which is inside the bracket, that is inside the coordination sphere. So this copper is attached to 4 ammonia molecule, and outside the bracket there is a sulfate ion, that is SO4 negative. So what happened in this complex cation is a complex and your anion is simple, that is SO4 negative. So this is an example of a cationic complex. Now next is ligand. This is also a general term that is used in coordination chemistry. What do you mean by ligand? The molecules or ions which possess lone pair of electrons, they are called ligands. So any molecule, any ion which have a lone pair of electron, that is called ligand. So it will donate these electron to the central metal atom and form a coordinate covalent bond. Now there are 3 types of ligand: negative ions, positive ions, and neutral molecules. In negative ion, there are some example. For example, cyanide, Cn negative, NO2 negative nitrite, OH negative hydroxide, NO3 negative nitrate, F negative fluoride, Cl negative chloride, Br negative bromide, O2 negative oxide. In positive ions, they are example for NO positive nitrocilium ion and 2H5 positive hydrazinium ions, and neutral molecule CO carbon monoxide, NH3 ammonia, H2O water, NH2OH hydroxylamine, CH3NH2 methylamine. So this is the example of a neutral molecule. Now types of ligands. Now ligands are of different types in this. First is mono or unidentin ligand. Now what do you mean by monodentin ligand? The ligand or ion which has only one donor atom or one point of attachment and can coordinate with the metal ion at only one site in a complex is called mono or unidentin ligand. Dentin means two-thread. Now for example, NH3 has only one donor atom, that is a nitrogen atom. It can be linked to the metal of a complex only through nitrogen atom. Now if there is a linkage only through one atom, then it is is in the example of monodentin ligand. For example, Cl negative, OH negative. In Cl negative there is only Cl atom which is capable of donating electron to the central metal atom. In OH negative there is a one atom which donated the electron to the central metal atom, that is oxygen. In H2O, in water also there is a one atom which donate electron, that is oxygen, because oxygen they have a lone pair of electron on it. So it is also possible that a monodentin ligand they may have more than one free electron pair. So they may simultaneously coordinate with the two separate metal atoms, making a bridge between them. Okay, so when they make a bridge, then they are known as bridging ligands, or you can say the bridging complexes. Next is polydentene ligand. The ligand or molecule or ion which has two or more donor atoms or points of attachment and can be linked to the same metal in a complex at two or more sites is called poly or multidentine ligand. Now in this there are different types of ligands. If the number of donor atoms they are 2, then that is bidentate ligand. Bi term is used for 2. If the number of donor atoms they are 3, then we say tridentate ligand. For 3 we use tri term. And if there are 4 donor atoms, we will use the term tetra. If there are 5 donor atoms, we will use the term penta. If there are 6 donor atoms, we will use the term hexa. So let's take the example of these type of ligands. Now, so the ethylene diamine, that is EN molecule, they has 2 nitrogen atom, 2 points of attachment. If you see this structure, NH2, CH2, CH2, NH2, they has 2 nitrogen atom. One is here and one is at the, so I will show you here. So one nitrogen is this one and one nitrogen is this one. So the 2 points of attachment with the central metal atom. So each nitrogen atom they can donate a pair of electron. So this is an example of a bidentate ligand. Okay, because there are 2 donor atoms here. So if you see the second example, that is an example in which En is attached to the central metal atom, that is copper. So each ethylene diamine molecule they form 2 coordinate bonds with the copper ion, forming a heterocyclic ring. Hence ethylene diamine is a bidentate ligand because they have 2 donor atoms. So next take the second example, ethylene diamine tetraacetate, that is EDTA. EDTA you already used in your labs for the titration, for the estimation of calcium, magnesium. EDTA is used. So EDTA is an important hexadentate ligand. It can bind to the same metal ion in a complex through 6 donor atom. So in this EDTA there is a 6 donor atom which donate electron to the central metal atom. So because of the presence of 6 donor atom, it comes in the category of hexadentate ligand. So here, what are the donor atoms here? 1, this nitrogen, second nitrogen this. Okay, these are the 2 donor atoms. Then fourth one, this is third one, then fourth one, fifth one and sixth one. So these are the 6 donor atoms which is donated electron to the central metal atom. So some polydentene ligands they have flexidentine character. A polydentene ligand may not necessarily use all its donor atom to get coordinated to the metal ion. Now these are the example: monodentine ligand, water, ammonia, that is the example of monodentine ligand. Bidentine ligand, ethylene diamine, oxalato, dimethyl glyoxymato, that is the example of bidentine ligand. Tridentine ligand, diethylene triamine, and tetra, that is triene. And tridentine ligand, this is also an example: tetra, triene, that is triethylene tetramine, hexadentine ligand, that is EDTA, ethylene diamine tetraacetate. So next type is the ambidentine ligand. If a ligand has two or more donor atoms, but while forming complexes, only one donor atom at a given time is attached to the metal, then it is called an ambidentine ligand. For example, in NO2 negative, there are two donor atoms. One is nitrogen and one is oxygen. Now, but at the same time, at one time, only one atom, they will donate electron to the central metal atom. For example, if oxygen is donating electron to the metal atom, then we will say M bond ONO. If nitrogen is this donating electron, then we will say nitrogen is donating electron to the central metal atom, then we will write M bond NO2. Similarly, SCN negative, they has two donor atom, one is sulfur and one is nitrogen atom, but one can be linked to the central metal atom at a given time, either sulfur or nitrogen. So if metal is bonded to sulfur, then we will say metal bond SCN. If metal is bonded to nitrogen, then we will write NCS. Okay, so M, that is your metal, they bonded to the nitrogen of the NCS ligand. So that is the example of ambidentine ligands. Now next term used in a coordination chemistry is coordination number. Now what do you mean by coordination number? The number of ligands that is directly bonded to the central metal atom is called a coordination number. Means how many ligands they are surrounding the central metal atom, that is the coordination number of that compound. For example, in this compound K3FeCN6, in this iron is surrounded by 6 cyanide ligand. So the coordination number of this compound is 6. If you see the another example of platinum complex PtCl2NH3 twice. Now in this the coordination number is 4. Why? Because platinum is surrounded by 2 Cl negative ion and 2 ammonia molecule. Therefore the coordination number is 4. Next example is cobalt example. In this cobalt is surrounded by 6 ammonia molecule. Okay, that's why the coordination number of this compound is 6. So the number of ligands which surround the central metal atom is the coordination number of that compound. Now in metal chelates, chelates means the complexes with polydentine ligands, they form a big ring-like structure that is known as chelates. So when metal they are bonded to a polydentine ligand and form a big ring-like structure, then we will say it is a chelate compound. So if a polydentine ligand is attached to the central metal atom, for example Cu, En twice 2 positive. Now in this the ligand is ethylene diamine. Okay. Now ethylene diamine is a bidentine ligand because it contains 2 nitrogen atom. The number of donor atom, that is 2. Okay, and 2 En molecule that is surrounded to copper metal. So in case of that type of ligand, when polydentine ligand that is attached to the central metal atom, then how we will see the coordination number? Okay, so in this the coordination number depend upon the number of donor atoms. The number of donor atoms which is present in the ligand. Okay, so the number of ligand is 2, but the coordination number of copper 2 plus is 4 because the number of donor atoms in the ligand that is 4. Each En contains 2 nitrogen atom. So 2 En will contain 4 nitrogen atom. Therefore the coordination number is 4. Next term, that is the coordination sphere. a coordination compound that is usually represented with the central metal and the ligands linked to it in a square bracket. So generally we will use a square bracket, that is the coordination sphere. Okay, so the complex, the metal atom that is linked to the central metal, that is linked to the ligand, inside this bracket is a inner coordination sphere, or you can say inner sphere. The group or ions outside the square bracket, that is the ionization or outer sphere. For example, in this example, if you see the copper NH3 4, that is inside the bracket, so this is a coordination sphere, inner sphere, and SO4 that is present outside the bracket, so this is a outer sphere. So this is a ionization or outer sphere. So next is a characteristic of a complex ion. The central metal ion in a complex is usually a transition metal. This is because the stable complex ion, they are formed by the metal which have a small ionic size, high charge, having large charge to radius ratio, make available suitable orbitals of appropriate energy to accommodate the electrons donated by the ligands, and exhibit multiple oxidation state. So second characteristic of a complex, that is once an ion form a complex ion, it loses its individual property and acquires the property which are characteristic of the complex ion. For example, when ferrous ion, that is Fe2 plus ion, they form a complex, it loses its individual property and will not give any test for Fe2 plus ion. Thus, Fe2 plus will not precipitate as FeOH twice on addition of NOH if you are adding sodium hydroxide to this, but solution of potassium ferrocyanate will give brown precipitate of copper ferrocyanide with copper sulfate solution. Once they will form a complex ion, they lose its individual properties, because after forming the complex ion, they will not dissociate into its ions. So they will not show the characteristic property of that ions. Next property is the complex ion retains its identity in solution though it may undergo slight dissociation. The degree of dissociation depends upon the strength of the bond between the central metal and the ligands. For example, the ferrocyanide ion is a very stable complex ion and undergoes slight dissociation. But if you see cobalt complex, that is cobalt SeN42 negative, is less stable and undergoes extensive dissociation. The fourth point is the net charge of the complex ion is the algebraic sum of the charges of its constituent ions. For example, the ferrocyanide ion, that is FeCN64 negative, that carries a net charge of 4 negative. This is because ferrous ion carries 2 positive charge and each cyanide ion 1 negative charge, thus giving a net charge of +2 plus -6 of -4, that is to ferrocyanide ion. Similarly, net charge of this complex is +1. The fifth characteristic of the complex ion, a chelate complex is more stable than a complex which is similar but non-chelated. So if you see this zinc first complex, that in this zinc is attached to ethylene diamine. So in this is a chelate complex, and when zinc is attached to the ammonia, that's a non-chelated complex. Also the chelate complex, they are more stable than a complex which is similar but non-chelated. So in the next lecture, we will discuss the nomenclature of coordination compound, how to name the coordination compound, that we will discuss in the next lecture. Thank you.